Houston, this is Station Commander. We have a priority medical situation. A crew member is in severe distress, possible urinary stones. They're immobilized and experiencing significant pain, requesting immediate guidance.
Copy, Station Commander. Confirm that there is no urologist aboard. Begin assessing pain levels and administer available pain relief protocols. Stand by for further recommendations.
Understood, Houston. This could escalate quickly. We need a solution now. Please advise.
Imagine you're on a deep space mission millions of miles from Earth. The isolation, the weightlessness, and the sheer distance amplify every challenge. Suddenly, a crew member is doubled over in pain. The diagnosis? Urinary stones. What may be a manageable condition on Earth becomes a critical threat in space, jeopardizing both their health and the mission itself. Think about it. Without a trained urologist on board, what happens next? This is where innovation steps in. Picture for a moment a technician equipped with an AI-guided system, autonomously performing shockwave lithotripsy, literally fragmenting the stones into passable pieces and resolving the risk to the crew member and the mission. This means no specialist needed, just cutting-edge technology enabling effective care. It's a remarkable achievement well within our grasp, ready to become reality with the right focus and unwavering determination. The approach we'll discuss today offers more than a solution for space missions. It could reduce treatment complications, lower costs, and ensure accessible AI-driven care, even in the most resource-limited environments. This presentation invites you to reimagine how we deliver healthcare in the most challenging conditions. Ready to learn more? Now, it's important to note that microgravity doesn't just alter how we move, it profoundly impacts human physiology. Bone resorption, the breakdown of bone tissue, releases calcium into the bloodstream, which is then excreted through the kidneys. This process significantly increases the risk of stone formation, a condition that's both painful and dangerous in deep space. This isn't just theory, it's supported by hard evidence. After just 111 days in space, a cosmonaut was found to have developed a urinary stone. And during the Skylab and International Space Station missions, 14 episodes of stone formation were documented among astronauts. These examples highlight an undeniable reality. Urinary stones are not a hypothetical risk. They're a recurring issue in long-duration missions. Without immediate access to specialists, these stones could immobilize crew members, jeopardizing their health and potentially derailing entire missions. But the implications go even further. Addressing this challenge is about more than mitigating a single medical risk. It's about ensuring that space travel becomes safer, enabling us to go farther and achieve more. And it's about leveraging innovation in healthcare to unlock solutions that could benefit humanity, not just in orbit, but on Earth as well. With this foundation of evidence, let's now explore the underlying mechanisms of microgravity, bone resorption, and shockwave lithotripsy to see how advanced technology can rise to meet this challenge. To fully understand the challenge we're addressing, let's examine how the crew member formed urinary stones in microgravity. In space, bone resorption releases calcium ions into the bloodstream. Under normal conditions, the crew member would have processed this calcium and then excreted it through the kidneys. But in microgravity, the balance of chemical concentrations shifts, leading to a condition called supersaturation. Supersaturation creates the perfect environment for crystal nucleation, where calcium begins to form small clusters, eventually growing into urinary stones. Here you can see a schematic illustrating this process. On the left, a normal kidney allows urine to flow freely, shown here as yellow dots. On the right, you'll see the impact of stones. One stone is blocking the flow entirely, creating a dangerous buildup of pressure and pain. This blockage is precisely what shockwave lithotripsy is designed to resolve. Using high-energy shockwaves, this technology fragments stones into smaller, passable pieces, restoring normal flow and alleviating the medical risk. This process is not only life-saving for astronauts in space, it's the key to self-directed, autonomous care in extreme environments. Let's take a closer look at how this innovation works. In this schematic, we can view the shockwave treatment. Here, the left and middle figures showing shockwaves directed at lower stone, and the right figure shows that the urine flow is restored. Here's how it works. Stone lithotripsy treatment employs high-energy shockwaves to fragment stones into smaller, passable pieces that are less than 4 mm in diameter. During treatment, between 5 and 25 shockwave applications are delivered. Standard protocols rely on administering 2,000 to 3,000 shockwaves per session based on stone size and location and patient characteristics. The problem is that too few shockwaves may leave stones too large to pass, while excessive treatment can cause tissue damage or hematomas. While shockwave lithotripsy is an established treatment, it's not without challenges. The key to its success lies in precision, delivering the right number of shockwaves at the right power level to effectively fragment the stone without damaging surrounding tissue. But here's the problem. Too few shockwaves? The stone remains too large to pass and the patient remains in pain. Too many shockwaves? There's an increased risk of tissue damage, internal bleeding, and complications. How do we optimize treatment, especially in deep space, where every intervention must be precise and efficient? This is where AI-driven technology changes the game. Instead of relying on fixed, generalized protocols, an AI system analyzes real-time imaging to track stone fragmentation progress. It adjusts shockwave intensity, rate, and duration dynamically, in real time, ensuring treatment is both effective and safe. And most importantly, it notifies the operator when to stop, eliminating the risk of over or under treatment. This is more than just an improvement, it's a breakthrough in autonomous medical care. Now let's go deeper into how this AI-driven solution actually works. 3 new metrics were developed. 1. Percent of stone loss. This metric acts as a real-time indicator of fragmentation. As the stone breaks apart, an algorithm continuously calculates how much of the stone has been successfully reduced. 2. Stone probability. This is powered by a convolutional neural network, a deep learning model that identifies and tracks stones during treatment. It ensures the correct target is being treated and differentiates between residual fragments and surrounding tissue. 3. Notification system. The AI monitors all variables simultaneously and alerts the operator the moment optimal fragmentation is reached. This prevents unnecessary shockwave applications, reducing the risk of tissue damage. Now let's take this a step further. AI-driven control of shockwave parameters. While real-time monitoring is crucial, the next breakthrough is full automation, where AI doesn't just track progress, but actively controls the shockwave settings for maximum efficiency. Power level, shock rate, and shock count are dynamically adjusted based on 1. Stone size. Larger stones are adjusted by AI based on stone density. 2. Stone composition. Different mineral structures respond uniquely to shockwaves and AI optimizes for precision and safety. 3. Patient-specific characteristics. Factors such as body mass index and age are automatically optimized for shockwave procedures using AI. The new approach unites 2 components: the monitoring stone status, like the stone area loss and stone probability, and AI predictions of shockwave parameters. A crew member experiencing severe urinary stone pain is carefully positioned in the spacecraft's medical bay. In microgravity, traditional examination tables are not an option. Instead, the patient is secured within a stabilization framework, ensuring they remain in a controlled, stationary position for treatment. Without access to a urologist, the AI-integrated system will guide the operator through every step of the procedure. Here is a simulation of how it could work for deep space missions. First, as noted, the patient is stabilized. Second, the operator selects the stone to be fragmented. The urinary stone is seen in crosshairs. The operator hovers the cursor over the stone and the probability of a stone is displayed. The stone is enlarged in the left inset. The operator clicks on the cursor and the stone image is boxed. The screen for selecting the stone presents a stone image which is saved and always shown in the top right for future reference. Third, shockwave applications can begin. Here is the control screen the operator sees. In this scenario, the stone is 9 mm in width and height and is located in the upper calyx of the kidney. The slide shows the found stone, which is highlighted in a green box. Lower inset shows magnified box stone. Upper inset shows the initial box stone. Stone loss is 0.00% because shockwaves have not been applied. Stone probability of the green box is 1.0, meaning that the probability that a urinary stone is in the box is 100%. The notification system shows green, which means go for shockwave application. The yellow text displays the AI-driven shockwave parameters for the first application. The power level is set to 1, the shock rate is set to 60, and the shock counts is set to 100. The cumulative shocks will be 100 after the shocks have been implemented. After the first shockwave application, the initial stone loss is 36.1%. Note subtle differences in the insets. Stone probability of the green box is 1.0, meaning that the probability that a stone is in the box is 100%. The notification system displays green, which means go for shockwave application. The yellow text displays the AI-driven shockwave parameters for the second application. The power level is now set to 2, the shock rate is set to 60, and the shock counts is set to 100. The cumulative shocks will be 200 after the shocks have been implemented. After the second shockwave application, the initial stone loss is 42.7%. Stone probability of the green box is 1.0. Note subtle differences in the insets. The notification system displays green, which means go for shockwave application. The yellow text displays the AI-driven shockwave parameters for the third application. The power level is now set to 3, the shock rate is now set to 90, and the shock counts is set to 100. The cumulative shocks will be 300 after the shocks have been implemented. After the third shockwave application, the initial stone loss is 49.7%. Stone probability of the green box is 1.0. Note subtle differences in the insets. The notification system displays yellow, which means caution for shockwave application. The yellow text displays the AI-driven shockwave parameters for the third application. The power level is now set to 4, the shock rate is set to 90, and the shock counts is set to 200. After the shocks have been implemented, the cumulative shocks will be 500. After the fourth shockwave application, the initial stone loss is 52.3%. Stone probability of the green box is 1.0. Note subtle differences in the insets. The notification system displays yellow, which means caution for shockwave application. The power level is now set to 5, the shock rate is set to 90, and the shock counts is set to 500. The cumulative shocks will be 1,000 after the shocks have been implemented. After the fifth shockwave application, the initial stone loss is 54.9%. Stone probability of the green box is 1.0. The notification system displays yellow, which means proceed with caution for shockwave application. The power level is now set to 6, the shock rate is set to 90, and the shock counts is set to 500. The cumulative shocks will be 1,500 after the shocks have been implemented. After the sixth shockwave application, the initial stone loss is 59.8%. Stone probability of the green box is 1.0. The notification system displays red, which means shockwave applications should stop. The power level is now set to 6, the shock rate is set to 90, and the shock counts is set to 500. The cumulative shocks will be 2,000 after the shocks have been implemented. By integrating real-time stone tracking with AI-driven shockwave control, we can answer the call for space crews who are in trouble and need urgent medical care. This dual capability holds immense potential not only for space missions, but also for remote healthcare on Earth, where specialist access is limited. Further research and validation are needed, but AI-driven shockwave lithotripsy marks a pivotal step toward autonomous deep space medicine. As we push the boundaries of space exploration, the need for autonomous medical solutions becomes ever more critical. Thank you for being part of this journey to shape the future of deep space medicine.